Okay, I think we are live. Hello, everybody. Welcome to the Latin American webinar of physics cycle. Today we are again with a very interesting webinar on high energy physics, especially related with experimental physics with the Atlas detector. So today, guest we have Dilia Portillo. She is a postdoc at the TRIUMF laboratory in Canada, in Vancouver, but she is based at Geneva, working on the Atlas detector at CERN. Exactly. And of course, she obtained the PhD title in the University of La Sorbonne in the laboratory of LPNH in Paris. And after that, she did a postdoc at Grenoble in France. And today she's here with us, and she's going to talk about the dark showers and the search of the resonant production of dark quarks at the Atlas detector. So Dilia, welcome to lawphysics, and please.
Thank you very much, Roberto, for the introduction. And yeah, thank you very much for inviting me. I'm super happy to be here and to discuss a bit of what I have been doing in the past couple of years. Let me share my slides. Let me know if everything looks good for you. Is okay? Okay. So yes, I will talk about dark showers and in particular a search for a resonant production of dark quarks with the Atlas detector. So, okay. So basically, this is the outline of what I will discuss. I will give an introduction of the dark matter searches at LHC that has been usually the weakly interacting massive particle paradigm and how we look for this WIMP in very classical searches and how we can take a new direction in which we are going to talk about the dark sector, in particular the dark QCD and what could be the signatures that we are hoping to see at LHC, and in more details on the search for dark jets with the Atlas detector. Good, so okay, let me introduce a bit the dark matter problem. So we have evidence of dark matter that it's, well, we have gravitational, well, galaxy rotation curves, we have galaxy collisions with X-rays, or we can have, for example, gravitational lensing, and all of this evidence of dark matter is inferred from this astrophysical cosmological observation. So this imposes an empirical problem of our standard model of particle physics, because there is no dark matter candidate within the standard model particles. There is no explanation of this dark matter. There is no particle that is electrically neutral, that interacts very weakly with the other particles, and that is very massive and stable. So a possible solution of this empirical problem that have been guiding our search for dark matter is the weakly interacting massive particle, or the WIMPs. So dark matter that has weak standard model interactions. And these WIMPs can be detected in a variety of experiments. So for example, here you can see the very classical view diagrams of how we can detect dark matter. One is the indirect detection, in which dark matter particles can annihilate and create standard model particles. So we detect the annihilation products of this dark matter. And okay, all of these circles or blobs are picture of our ignorance, are like what will be this dark matter to a standard model interaction will be that we don't know. Then we have direct detection, in which a dark matter is recoiling as with a standard model particle, and here we're going to concentrate in the colliders and accelerators search for dark matter, in which these standard model particles interact somehow and produce standard model particles. Or even we can check the existence of dark matter or infer it with standard model particles that we will discuss later. So, okay, so we want to concentrate in this collider and accelerator way of detecting dark matter. So for this, let me introduce the ATLAS experiment at the LHC. So the Large Hadron Collider, this LHC, is a huge 27-kilometer circumference circular accelerator here in the frontier of France and Geneva, and is providing collisions every 25 nanoseconds, and is designed to achieve very high center of mass energy and high luminosity. And here in the analysis I will discuss, we are going to consider the run 2 data and run 1 data that goes from the beginning of the LHC until 2018, with a total luminosity of 140 inverse femtobarns. And this ATLAS detector is one of the general purpose detectors, a CMS, that has almost 4 pi a solid angle curvature detector optimized for multi-TV proton-proton collisions. And ATLAS detector has this very onion shell structure, in which in the very close part to the proton beam, we have the inner detector, then we have the calorimeters. So in the closest part of the inner detector, we have the electromagnetic calorimeter, then we have the hadronic calorimeter, and in the outermost part, the muon detectors. So, okay, so how we can produce and detect this dark matter at LHC? Okay, how we can detect dark matter with ATLAS experiment? So if we assume that the standard model interacts with dark matter, that there are some standard model to dark matter interaction, like in the weakly interacting massive particle models, the LHC may be able to produce these invisible particles, these dark matter particles, in very controlled conditions. So let's imagine the basic diagram of a dark matter production and detection. So we have the 2 protons, so let's imagine quarks that somehow interacts and then produce a pair of dark matter. But we know that this dark matter particles does not interact with the detector. They are neutral, they are stable, at least in the dimensions of the detectors. So at the end, in the transverse plane of our detector, what we will see are 2 invisible particles, so we will not see anything. So then, how we can trigger these dark matter events? And for this, we use the mono-X topology, what we call the mono-X searches, or the MED plus X. So this searches or topology considers a very well-defined standard model particle that we call X, and it is recoiling against large amounts of missing transverse momentum. So let's imagine, again, we have 2 quarks that then somehow interact and produce a pair of dark matter particles, and in association with a standard model particle that we call X. So in the final state, we will look for missing transverse momentum coming from the dark matter pair production and a well-defined standard model X. So here you can see the standard model particle X recoiling against the dark matter pair production. Or there is another perspective of this, is to search for the mediator. So we have a look at what this blob of ignorance that we have here, what will be the interaction. So we say, okay, let's have a mediator that connects the standard model, the visible sector, with respect to the dark matter sector, and we search for this mediator. So we can prove the dark matter interaction even if dark matter is inaccessible with our detector, and we can look for both visible and invisible decays of this mediator. Okay, so this is a very canonic event of what will be a mono-X topology. We have a lot of hadronic activity here in the upper part, and then nothing in the opposite side. And this could be, well, that this nothing, this energy that we are missing is coming from the dark matter per production. And well, okay, for this, we need to do an analysis, check a lot of different events, because there are a lot of background events that can resemble this kind of topology. For example, a Z boson decaying into neutrinos. The neutrinos are not recorded by the ATLAS detector, so we can still have nothing, missing transverse momentum in one side and a jet in the other side. So these 2 objects, these 2 reconstructed objects, the jets, and the missinity are key elements for dark matter searches in general in the Atlas detector. So let's go a bit into the detail of the missing transverse momentum. The missing transverse momentum uses the fact that in the transverse plane of the detector, the momentum is conserved. So this means that the vectorial sum of all the objects in the final state in the transverse plane should be equal to 0, the vectorial sum. But when we have that something is missing, for example, a dark matter candidate, then we have this missing transverse momentum. And this missing transverse momentum is reconstructed using the muons, electrons, photons, taus, jets, and even soft activities that is not related to any of the previous mentioned reconstructed objects. So we take the momentum of all the objects, we sum them, and the missing transverse momentum will be what we are missing for this momentum to be 0, for the total momentum to be 0, for the total momentum to be conserved. So this is the missing transverse momentum, or the MET. We also call it MET. A second object that is important is the jets. So we have all this hadronic activity in the upper part. And okay, but what is this jet? We know from QCD that there is color confinement. So these quarks and gluons that are produced after the collision will not freely travel, but they will rapidly, immediately shower and hadronize into collimated bunch of particles. So we have that these quarks and gluons, which are the ongoing factor, will fragmentate and create hadrons or colorless states. And for this, well, we reconstruct them as jets. And the jets basically represent the shower produced by the hadronization of this quark and gluon. And a jet can be formed by any form momentum. So we can have track jets, we can have calorimeter jets, we can have even simulated particle jets. But okay, in Atlas, in order to reconstruct onto the jets, we use calorimeter deposits, so energy deposits in our calorimeters. And we take these 4 momentums, and with a jet algorithm maps this set of 4 momentums into a set of jets. And depending on our physics intent of what we are looking for, we can use different size of the jet radii. So for example, if we have quarks or gluon, we can use small radius, but if, for example, we have very heavy particles as W, Z, Higgs at high Lorentz boost, they can be reconstructed with a large radius jet. So this is a very important object as the missing transverse momentum. So now that we know that how to reconstruct them, so how these mono X searches strategies goes. So first, what we want to do basically here is to look for an excess in the energy imbalance in the transverse plane. And we know that this is called missing transverse momentum. So first, we want to select events with high purity of the X particle coming from the standard model, which is the visible part of the event, and it is recording against high amounts of missing transverse momentum. And the goal is to search for an excess at high missing transverse momentum tail. So our signal is expected to have high missing transverse momentum, so we search for excess with respect to the standard model prediction at high MET. So the canonic search is when X is a gluon, which is what we call the mono jet. So we have a gluon initial state radiated, and then we have a very energetic jet recording against missing transverse momentum. This is the event display that we saw before. And here you can see how the missing transverse momentum look like for data simulation, where you can see for simulation all the different histograms of the backgrounds of the standard models. And for the monojet searches, signals, we can see these dashed histograms that as you can see, at higher goes the missing transverse momentum, the higher is the signal to background ratio. So we try to look for an excess here, but here you can see that no excess is observed with respect to the standard model prediction. So we haven't seen yet dark matter in the monojet signature. Good, so now, if I am able to pass the slide, yes. Okay, so this has been the weak scale paradigm. We have been looking for this weakly interacting massive particle for about the beginning of the LHC, the beginning of operations of the LHC. And what has been done is that we are having this WIMP under assault. Here you can see that the complementarity of the different searches we do in Atlas in the plane of the mass of the dark matter candidate against the mass of the mediator. And in yellow are the mono X topologies, and in blue on the back are all the digest searches, for example, that are mostly cover all the parameter space, okay, with the caveat that here we are selecting some doing some assumptions of what will be the couplings. But okay, you can see that basically a lot of the parameter space is excluded in these cases for both mono X topologies and for mediator searches. And also if we look, for example, at the complementarity with respect to direct searches of our Atlas searches, here you can see that again, a lot of the parameter space is already excluded, but there is still a very nice complementarity with respect to direct searches. But what we can see here is the WIMP miracle and its observability has guided the choices that we do for how we search for it in the experiment and what are the theories that we assume for interpreting our signals. So what we have now is that the WIMP paradigm is in tension, and many of the parameters of those simplified models that we have been studied for more than a decade has been now excluded. So maybe it's time to think of different directions. What we have now is what dark matter probably is not. We have seen dark matter in the sky. We have gravitational lensing, we have collision of galaxies, rotation curves, okay. But we have not seen dark matter in the lab yet. What we have is a lot of excluded parameter space. But still, it's important to look for, well, this motivates us to look for signs for new physics that has been escaped our current constraints. And they can be outside our current constraint because we haven't not looked yet for this kind of signals, or because these signals doesn't not fit our preconceived notions of how this new physics should look like. So, and maybe we can think of then a dark sector. Why? Because, okay, we know that the standard model is a bit complicated. 15.5% of the ordinary matter is the standard model. So we have this puzzle that, okay, has been solved with the Higgs, and then 15.5% is this zoo of particles. Then, why we should expect that 5 times the universal energy budget of the standard model to be less complicated than this, to be just one particle, one dark matter particle, which corresponds to 84.5% of the matter of the universe. So why not to think of a dark sector, a dark hidden sector that has confining dynamics that could yield also a zoo of particles, as we already have with the standard model. And this can also yield very different collider phenomenology than what we might expect and what we have been looking for already. So, okay, this dark sector, how complicated could be this dark sector? We have no clue. The imagination and the creativity is the limit. We haven't discovered it because maybe this dark sector is hidden far away in a hidden valley, a scenario that is accessible at very, very high energies, which are not the current energies in our collider, and has some kind of confining dynamics. So it could be similar to the QCD of the standard model, SUN symmetry that we can call dark QCD, that maybe can have dark hadrons, so they can bind into dark hadrons, and one of them can be a good dark matter candidate, and now there is a place for our dark matter particle or our dark matter candidate to be in some sort of new puzzle. But okay, this dark sector could be completely hidden, and okay, we cannot access it. So in order to access it, we need a portal. a portal that connects the standard model with this hidden sector. So we assume that this dark sector communicates with the standard model, the visible sector, with a mediator that is charged both under the standard model and the hidden sector. So, okay, basically, in this dark QCD that we are going to consider here is a SUN gauge theory in which our dark quarks confined below some confinement scale lambda d. And this will be more or less what will be a dark shower. So we have first the production. The production with a heavy state, which serves as a portal, for example, a Higgs, a C prime, a scalar, and then this mediator or this portal decay into the dark sector. Then what happens into the dark sector is that these dark states can shower and hadronize, leading to some kind of dark jets, or it can be not even that they produce collimated shower of hadrons. They can be also soft radiation patterns, but we will not discuss this here. And then these dark hadrons can decay back to the standard models, or can remain stable, can remain invisible, or even some of the dark hadrons may have a significant lifetime. So this is what we call the dark showers. And these dark showers can give us different signatures that we can look for in our detectors. One is the emerging jets. So let's imagine this axis, vertical axis, in which it shows the distance with respect to the interaction point of the majority of the jet constituents. So we have some dark hadrons in these emerging jets that may have a significant lifetime. So since they have a significant lifetimes, and you can see it more or less here, there is a notable distance between the interaction point and the decay point. So we have jets that starts to emerge in our detector. So we have this place vertex, and these are the emerging jets, and currently Atlas is in process of doing a search for these emerging jets. And we can think of another axis of these possible dark shower signatures in which we consider a new variable, the R invisible variable, which is defined as the number of stable hadrons over the number of total hadrons. So the ratio of invisible particles inside the jet. And for this, we have semi-visible jets, in which some of the dark hadrons may decay to visible to the standard model particles, but others can remain stable and remain invisible. So we can have jets with a mixture of visible and invisible hadrons, or well, components. And for this, Atlas performed a search that actually 1 month ago was published. And it's, well, the semi-visible jet, you can see here an even display of what semi-visible jet candidates looks like. This is for 2016, where we have the 2 candidates of semi-visible jets. But what is interesting in this search is that since some of the hadrons inside the jets remain invisible, the missing transverse momentum will be in the direction of one of these jets. And this makes this search very challenging, because usually this is the kind of jets we discard in Atlas, because if you have missing transverse momentum inside the jet, it means that your jet is not well measured. So it was quite challenging, and let me give you a bit of an overview of how this semi-visible jet analysis goes. So in this analysis, they consider B fundamental T-channel scalar. So we have this new scalar that couples to the quarks and to the dark quarks, and then this dark quarks goes into the dark shower, and some of the hadrons inside this dark shower can decay back to visible particles, and some other don't decay back to the standard model. And this is how invisible is your jet, is parameterized with this R invisible variable that can goes from 0.1 to 0.99 in this analysis. And basically here, what we want is to select events with at least 2 jets high missing transverse momentum and that there is one of the jet close to the missing transverse momentum in the azimuthal angle, this phi. And in our signal region, we want to have very high missing transverse momentum. We don't want any lepton. And this HT variable that I show here, greater than 600, is the vectorial sum of all the PT of the jets. So this means events with high hadronic activities. And then for estimating our backgrounds, we use control regions using different selections of muons to estimate C plus jet, W plus jet, and TT bar. And in this analysis, the important variables are the PT valence of the jet, which is defined here. And you can see here the PT valence distribution for simulation and data, and even for some semi-visible signals in dashed lines for this variable. And then here is the other variable, which is the difference, the azimuthal difference of the two jets, where you can see again simulation, data, and the signals. Where, for example, if you have a very high mediator with a not very high number of invisible particles inside your jet, it starts to be very close to each other, the two jets. So they use these two variables to do a simultaneous fit in the signal region and control region. And at the end, what they do is to put the exclusion limit, since, as you can see here, there is an excellent agreement between the data and the background prediction. So what we can do is to put exclusion limits in the parameter of this R invisible, where as higher we go, the more visible, the more invisible is, and as lower, the more visible, as a function of the mass of this B-fundamental T channel scalar. That, as you can see, that assuming a couple strength of unity between mediator and the standard model quarks, so this lambda, and the dark quarks, we can exclude masses up to 2.7 TeV, depending on this R invisible. So this is the semi-visible search. But there can be also another limiting case that we already discussed, in which this R invisible is equal to 1. So meaning that all the hadrons inside these semi-visible jets are invisible, sorry. So we have that basically we don't have a visible jet. So what we do here is a monojet search. So this jet can be initial state radiated, and this can be very similar to what we do in the WIMP-like monojet search, in which all the dark hadrons are stable, and the signal is very similar to the weakly interacting massive particle search that we already discussed. And then if we go into this corner where this R invisible is equal to 0, so it means that all the components inside these dark jets are visible. So we have basically a QCD-like visible dark jet. So this means that the dark hadrons decays promptly to the standard model. And at the end, these dark QCD jets will look like standard model QCD jets. And in this visible dark jet analysis or search that I'm going to discuss more in detail in the following, we have this C prime that mediates that connects with respect to the quarks of the standard model and the dark quarks. And then these dark quarks goes into the dark shower, and these dark hadrons will decay, most of them or all of them, to visible QCD jets from the standard model. So at the end, what we have is that we have two large radius jets in our detector. And this is a very brand new Atlas search that is going to be imminent in JHEP. It has been accepted. So a bit of these signal models. So we have that, okay, the C mediator that you can check out the benchmark models in this paper, where we have 4 benchmark models, A, B, C, and D, and all of them has higher running coupling with respect to the standard model. A and C with much more running coupling, meaning that they have higher confinement scale. And then since they have, well, and also they have negligible invisible fraction. So they have basically all of the dark hadrons are stable. And since they have higher running coupling and they go into this double hadronization, meaning that they have to hadronize in the dark sector first and then hadronize back to the standard model sector second, so they have higher number of soft particles that can translate also in high number of tracks, and these jets are very wide. And the signal that we generate are using the hidden valley module of PTI-8 that considers a SU3 symmetry, and we have different masses of the C primes that goes from 1.5 to 3.5 TeVs in beams of 250 at low masses and 500 GeVs at high masses. Good, so the general strategy for looking for dark jets. So for this, we need to reconstruct the jets first. And for this, we use calorimeter jets, large reduced jets, and we trigger on these large jets. And then we select events that has high PT, large reduced jet, that are central. And then our signaling scenario is to have 2 dark jets. So we have that the C prime decays into dark quarks, but at the end, these dark quarks, after the double hadronization, they are, for us, our signal are 2 large reduced jets. So first we need to tag them and distinguish them from the QCD jets. And then we want to look for a resonant excess in the dijet invariant mass above a smoothly falling QCD background. So you can see here the simulated background in red, the data in black points, and our dark signals in these different colors for the dijet invariant mass. And some characteristics. So the cross-section of these signals is arbitrary. So it depends on the C prime coupling. Then, so we can play with that. This lower bound on the dijet invariant mass is given by the trigger turn on. Then we already know that our signals are wide. You can see here that they are quite large or wide. They are 50%. And they are also shifted. For example, these signals are for 2.5 TeVs mass of the C prime, and they are not pointing at 2.5. They are pointing a bit below. And this beam size that we are using for the dijet invariant mass is approximately the expected resolution, which is 100 GeVs. So we want to look for a resonance, and hopefully our data looks like something like this for our signal dark jets above the standard model QCD background. So let's look first. Let's tag these dark jets. And this is very challenging because we know that they look like standard model QCD jets. So we notice that the group number of tracks, the number of tracks inside the jets, that's what we call N track, is a very strong discriminating variable, because we know that this dark jet has more soft activity inside them. So here you can see the number of tracks for the leading and the subleading jets, in again red for the background, and then in the different colors for our signal, where they are showing higher tails, they are showing higher number of tracks. So clearly, if we define a cut in N track, we will have a great way to discriminate the background in red with respect to our signal in the different colors. But the problem is that if we do this N track cut, this, for example, here, let's take a cut in 80. So we take most of this bulk part of the background and select the high N track signals. If we do a sharp cut and N track greater than 80, this will sculpt our background dijet mass spectrum. So with our normal selection, we have this smoothly falling, beautiful spectrum of the diegetic invariant mass. But with this cut, it starts to have a shoulder. And this makes the background estimation very difficult. So the challenge in this analysis is to find a variable that has this good background to signal discrimination as N-track, but without modifying the MJJ, the diegetic invariant mass distribution. So we defined a new key variable, which is called the N-track epsilon. This new discriminating variable N-track epsilon is constructed in such a way we can decorrelate the diegetic invariant mass with respect to which is decorrelated with respect to the diegetic invariant mass. So how we construct it? So we define a target efficiency of, for example, 1%. The efficiency is defined as the number of events that pass this N-track cut over the total number of events. And this is a target efficiency for the background. And then we take the MJJ, as you can see here, the diegetic invariant mass, we divide it in bins, and we take for the leading jet, we check for each of these bins the minimum value on N-track that leads to this 1% target background efficiency. So if we take, for example, this bin here, then we will need to do a cut in around, I don't know, 79 on N-tracks, so we can get a 1% background efficiency. And this number here is what we call the percentile, and is denoted as P. So we rinse and repeat. We do this for each of the diegetic invariant mass bins, and we draw these percentiles as a function of MJJ, as you can find here, for the leading jet. And then we repeat the procedure with the leading jet. And then, well, you can see here, for the leading in red and for the subleading in blue, and then we fit all these percentile values in order to have a very smooth fit as a function of the percentile, as a function of the diegetic invariant mass. And at the end, this N-track is defined as a function of MJJ, taking the N-track of the jet minus the percentile. So this means that we can have a signal region that is defined as having N-track epsilon greater than 0 for both jets. So we are going to have this N-track greater than 0 will mean that the N-track is greater than the percentile, so is giving us a background efficiency of 1%. So this provides, at the end, if we do this bin by bin, the same background efficiency in each MJJ bin. And at the end, this translates that the signal region, as you can find here, in red, is having the same, or mostly the same shape as as we expect in preselection. So the N-track epsilon keeps the MJJ shape mostly unbiased. So now we have this beautiful, smoothly falling multi-jet invariant mass. So we can easily, well, not easily, but it would be more easy to estimate our background. And this N-track epsilon, with this decorrelation method, help us to define different analysis region. So the signal region, we know, okay, is having N-track epsilon greater than 0. The validation region is having the subleading inverted, and a control region where both are inverted. And of course, this control region will be the multi-jet, the QCD background will be our dominant background here, and this will be dominant with signal region, and just 99.9% of the background will be rejected in the signal region. Good, so, but this N-track epsilon bring us challenges. We can't define them in full data, because if there is a signal, then we will cut harder in N-track, and then we will see a bump in the percentiles. And we can neither define a data control region to define this N-track epsilon, because this will change the MJJ distribution. So we need to define them in simulation in the Monte Carlo, and then apply it to the data. And this relies in a good description of the Monte Carlo in this N-track epsilon variable, which is more or less the case, at least in the region we are interested, which is at high N-track. But at the end, these data Monte Carlo differences will translate in difference in efficiencies in the cut when we apply it to data with respect to Monte Carlo, and in an imperfect decorrelation of the n-track epsilon with respect to the diegetic invariant mass in data. And because of this, we add systematic uncertainties on the background shape. Good. So now we tag our or identify our dark jets. And the second part of our analysis is to search for a resonance. And usually, okay, well, we know that our dominant background originates from multi-jet events, that we are looking to have a very smoothly falling MJJ spectrum. And usually in the dijet searches, what we do is to fit with a functional form because it's smoothly falling, very nice. But in the case of the dark jets, we know that they are very wide. They have large signal width, and then if we perform a direct fit using a functional form, what will start to happen is that our background estimation that you can see here in blue, as soon as we inject signal, this is pseudo data, we inject signal as if there will be dark jets, the background starts to accommodate this signal, starts to be concave. So we are losing here sensitivity. So the background is pulled by this possible signal. So we have this second challenge. And what we do now is to take the advantage that this n-track epsilon is decorrelated from the diegetic invariant mass, and we are able to define the control region in which we invert this n-track epsilon cut. And by construction, this n-track epsilon gives brings our background invariant mass distribution shape invariant, does not bias our shape. So the control region shape will be the same as we expect in the signal region. So we can take a background template from our control region. And here you can see how the control region in blacks look like with respect to the validation region to validate that is actually decorrelated. If you remember the validation region, has one of the n-track epsilon inverted. And here you can check that actually, yes, in the control region of validation, the shape is unbiased. So we can take the shape directly from the control region, and then we do a signal plus background fit, in which the background is coming from the control region, the normalization is floating, the signal shape is extracted from the simulation, the signal strength is our parameter of interest, and we perform the test in a validation region in order to check that our strategy was working. And okay, here we arrive to the results. So this is our data in the signal region. Here you can see the observed data compared with the data in the control region, which is normalized to the signal region expected yield. And we can see that, and here we run a Baumhunter algorithm checking if there is any deviation of the data, the black points, with respect to the expectation, the red distribution coming from the control region. And we can see that there is the most discrepancy is found in this window here with a p-value 0.6. So no significant excess was observed with respect to the background prediction. But here what we can see is very interestingly, let's look at this point, how it looks like in our detector, in an even display. So this point here that has the highest diegetic invariant mass is coming from 2018, where you can see, well, these are the two candidates for dark jets. And what is very interesting here to see is that inside this dark jet, there is a lot of tracks. Actually, it has like 80 and 90, if I remember correctly, tracks and tracks inside the jets. So charged particles, which is very interesting to see. And since we don't observe any discrepancy with respect to the standard model prediction, we can put exclusion limits. Exclusion limits in the upper limit on cross-section times branching fraction of the C prime decaying into dark quarks. For the different models, we consider A, B, C, and D. And then here you can see the expected, well, the theory line in red or in blue. And then one can have that the exclusion will depend on each of the model, but it can reach to 3 or 3.5 TVs for some of the models, where in which the usual digest search cannot say anything, which is very nice because we select couplings here of the C prime to dark quarks that are not yet excluded already by digest searches. So, okay, so now I arrived to my summary slide. So we know that there is evidence of dark matter and that it plays a critical role on the formation of the universe, but we don't know its quantum nature. So far, the experiment have not found any answer, and we have been gradually excluding different theoretical scenarios, which is okay, because excluding scenarios will help us to guide future searches and maybe take new directions. And here is a new direction, new perspective that is starting to be very popular at LHC, in which the dark matter lies within a dark sector, which is similar to the QCD sector in the standard model. And I presented in more detail the visible dark jet search, that is the very first search of a C prime resonance decaying into pair of dark quarks in the digest final state at LHC. And here we are using full run-to data. You can find here the archive. And here, basically, we look for resonance in the digest invariant mass using this brand new key variable, n-track epsilon, that is decorrelated from the digest invariant mass. And the signal region is defined with n-track epsilon greater than 0. And our background is estimated with a control region inverting this n-track epsilon. And since this is the first such search at LHC, so we already have a briefing feature in the Atlas web page that you can find here, which is more or less like a press release. So yes, so this is what I wanted to discuss today. Thank you very much. And yeah.
Thank you very much, Dilia. It is very interesting and hopefully, let's see if dark shower are found, and we can have an extra physics beyond the standard model and to understand what's happening with the dark sector, let's say. So first of all, for all the people that are following the live transmission, you can write the question for Dilia in the chat. So for the moment, we're going to start with some question from the audience here in Zoom. I don't know if Joel or Alejandro has question. Joel has a question. Please.
I have a couple of questions. Thank you very much for the talk. It was very, very, very nice. I enjoyed it quite a lot. So you have focused on the dark jets, but unfortunately I'm interested in the emerging jets. So I was wondering if you could give a bit more information regarding how, in what way are the emerging jets different from the displaced vertices? Because you said, okay, in the emerging jets, you get displaced vertices, but I don't know how they differ. The search for the displaced vertex differs from the one of the emerging jets.
Yeah, that's a very good question. For the moment, there is no emerging jet result in Atlas, and it's an ongoing analysis. So I cannot, I actually, I don't know, because if we look for displaced vertex, what is interesting here, maybe I can show in the displays, is that when we look for displaced vertices, is one displaced vertex where all the particles are coming from. So in usual searches for displaced vertex, we have the interaction point, then a vertex, and then from this vertex, the constituents or the jets or whatever you are looking for, it's coming from that second interaction point. In this, I think is much more challenging because there is not a unique secondary vertex. They are just that are emerging in different parts. And there is a decay chain of these dark hadrons inside this dark sector that has different lifetimes. So you can see here, for example, one that is very close, but one that is farther, another one that is very far. So it's not, it cannot be recast with a usual displaced vertex search. So that's why it has to be a very optimized search for jets that are emerging in different displaced vertex. But then the details on how they are thinking of doing this, I know that there is already a search for this on CMS that we need to take to look. I just have here the archive, but yeah, we will need to have a look more in detail. But yeah, I think it's quite challenging, and I am not super sure what will be the way of reconstructing the object such way you are having multiple displaced vertex.
Right, multiple ones. And I guess that, I mean, from the way that one would expect that with time, this emerging jet, you start, I mean, within the emerging jet, you start seeing a larger number of standard model particles as the jet develops. So I was wondering, maybe it would be also sensitive. I mean, searches using the muon chambers might be more sensitive to like trackless muons, or maybe checking the difference in the energy depositions between the HCAL and the ECAL. I don't know if those searches are also being used for the emerging jets.
Yeah, I am not sure. This is a homework for me because I don't know what is Atlas doing right now for the emerging jets. But
Yeah, I'm
yeah,
sorry. I'm just
no,
focusing
but
on
it's quite interesting question. And yeah, because I usually for displaced vertex, what we use is calorimeter deposits. But there could be some that develop in the muon spectrometer that, as you were saying, for example, here it shows one that is even inside the hadronic or the electromagnetic calorimeter. So I guess, yeah, one need to really check trackless jets or tracks of outside muon spectrometers that are not associated to the inner detector tracks, while not combined muons. Yeah, but I am not sure if they are going into those details, to be honest. For initial search, I will bet that is calorimeter jets, not taking into account inner detectors, which is complicated because usually in Atlas, we are using particle flow jets in which we have calorimeter deposits combined with inner detector tracks for run 3. So they have to develop an entire new object for the particular search and calibrate it. And yeah, and I will say they will start with calorimeter jets in this case, but I will need to check. Actually, super interesting.
No, it's been the talk has been fantastic. I'm very sorry, just that the part I'm most interested in is the one.
It's not yet published, and I am not aware, but okay.
I see. Okay, thank you.
Thanks to you.
Thank you, Joel. So at the moment we are waiting for some question from the YouTube in the YouTube chat. So also I have a question, Dilia, about in these scenarios in which the dark sector, the dark shower, and the dark quarks, let's say, are unknown with respect with the QCD counterpart. Yeah, let's say, and my question was about how the jets are created or modeled, because I remember that, for instance, to create jets in Monte Carlo, people use Pythia or Herwig, in which they have tuned how these jets are formed, the hadronization of the the leading quarks. So in this scenario, how it is the same procedure, just changing the coupling constant, or the topology of the jets also would depends of the complexity of this SUN.
Yes, so actually, yeah, there is a module, a PTIA 8 module that is called the Hidden Valley, where one can tune all of these different topologies. So what we use in semi-visible jets and in dark jets is this same PTIA Hidden Valley, which is currently under developing. So it's not, there is a lot of discussion from the theorists on how to actually model these kind of showers, dark showers. But for example, in the semi-visible jets, they use, well, okay, maybe I will discuss better the dark jets. So in the dark jets is a SU3. So in SU3, so I will say, but I am not an expert in Monte Carlo, that they have basically more or less the same structure as the SU3 QCD. So it's a SU3, and then we have tuned different parameters. So we have 3 quarks, but this lambda d, this confinement scale can variate. It could be 15 or it can be 2. So we have 2 different, but higher than the standard model. The mass of the dark quarks is tunable, the mass of the dark pions, the mass of the dark rhodes, and then how the dark pions decays. For example, in the models A and B, they can decay to quarks, but in the C and D, they decay to dark photons. So then you have a U1 extra symmetry, and these photons in the model C can decay leptonically in most of the cases, and in the model D, they decay into pions most of the cases. So this is modeled with this hidden value PTIA, which I think it's considering the parameters of the shower development and the partons and the hard scatter, everything quite similar to what we see in the standard model. Yeah, but this is a quite dynamic branch for these dark signals that is currently under discussion. Yeah.
Thank you. So another question, because here in another chat, they asked me if in this case of analysis, currently they are using, I don't know, a machine learning algorithm to optimize the search of the. I mean, one is the standard Monte Carlo, and then just to, but in this case of cutting edge physics, this type of algorithm are used for the optimize or to cut the parameter space to have what is only signal, what is the validation and the control.
Yeah, so since this is the very, very first searches at LHC, actually, the semi-visible is the very first search with a T channel, and the dark jet is the very first search with a resonance S channel. We wanted to keep it simple, so we can have a baseline search where we can optimize from it. So in the future, one can think, yes, for example, here, we are tagging or identifying this dark jet with the use of this fancy entrac epsilon, but we can make it more fancy. We can make, for example, a VDT that is trained with jet substructure variables, because at the end, what is giving us the highest discrimination power in this kind of dark shower searches are jet substructure, as is looking inside the jet. So we can use different jet substructure variables to train a VDT and to classify and help us classify signal with respect to background. And this is something one can explore. I think I have the feeling, maybe, let me search if I am not lying. Because, yes, for example, in the semi-visible jet search in CMS, which is different from the one from Atlas. The one from Atlas is a T channel. This is an S channel. They use a BDT for jet tagging the semi-visible jets. And they were able to select in this VDT classifier higher score of the VDT and then do a functional fit on the transverse mass. They were able to do a transverse mass because it's a S-channel mediator. But in the other case, it was a bit more complicated with a Binet likelihood fit. But yeah, this is starting to come up, and the baseline will be a BDT for sure. Then one can think graph neural networks on something more interesting for the future analysis. Yeah.
Okay, thank you. I don't know if there are other questions for Joel. Last minute question. You are okay. Okay, so for the sake of the time, we are arriving to the end of the transmission. So Delia, thank you very much for the webinar. The webinar is very interesting, especially also since it remains in the YouTube channel for the future physicists that are going to be interested in the topic. It's going to be a very useful reference to look. So for all the people that are following the transmission, we are arriving to the end, and we invite you to come for the next webinar that is in 2 weeks from Josu Hernandez. And you can follow us in our different social network and here in the YouTube channel just to keep updated about what is happening in physics and also with the people from the Latin American that are spread across the world. So thank you, everybody, and see you in the next time.
Thank you. Ciao.